last thing we're going to look at with the kinetic molecular theory is gas phase collisions. That's one other thing we can get a lot of information about with this model we have of random particle motion, where the particles are all bouncing around off of each other. Now there are two things that we can calculate, and let me first say why we're interested in this. If we think about two particles hitting each other, that's necessary to predict reactions, right? Because reactions can only occur when particles are actually able to hit each other. So if we know how often particles hit each other, it can give us an idea of how fast reactions will go. It can also tell us about lifetimes of reactive species, right? If something is going to react, if it collides with anything, then we can get a rough idea of how long it'll last in a given environment based on how long it'll go until it collides with something else. Right, so that can give us some sense there, and this applies to all sorts of different areas. So we can think about just the atmosphere, right, that we live in, but we can also think about things like outer space, where the gas pressure and density is much less than it is here on Earth, and so these collisions happen much less often, and it really affects the chemistry that happens out in space. We can also think about high pressure environments like inside of a car. A car engine, right? A combustion engine or anything like that. That's another thing that we can model with this sort of behavior. So there's two different things that we can calculate. The first is the collision frequency, and these are related to each other. They're not completely independent. But collision frequency, and the second one is what we call the mean free path. The collision frequency is how often do particles on average hit each other. Now, of course, any individual particle we look at will sort of have a random time, but if we're looking at average behavior, we can get an average. And the mean free path is how far, again, on average, does a particle travel before it hits something, before it hits either the wall or another particle. So, how are we going to derive these quantities? So let's imagine we have a particle, our gas particle, and we can think about, we're just going to imagine a situation where everything is the same. So we all have all nitrogen molecules and everything we assume is a sphere. This is the same assumptions we've had with the up to this point with kinetic molecular theory. Now this particle, if we imagine it traveling in one direction this way, it's going to trace out sort of this cylinder shape where anything inside of that cylinder will hit the particle. And let's imagine only our particle, right, this is the only moving particle here. And everything else is just fixed in space. And we can take it, we can add back in the other particles do move as well later. So if we have another particle the same size out here, that'll be a miss. If we have something that's in here, where any part of it is inside of here, this will be a hit. And if we have something right on the edge, this would be like a near miss. Right, and so this is, if you look in your textbook, this is figure 27.11. Okay, and so this area that's swept out, so the area here on the side of the cylinder, is what we call the collision cross-section. All right, and this is going to be equal, we call this sigma is equal to pi times the diameter of the particle squared. Diameter because it's not just the radius, right? If we use the radius, that would just give us the area of this, but we need to multiply that by 2. I haven't drawn this to scale. This should only be, right, this should be 2r here, which is equal to d. Right, so this area that's swept out is pi times d squared. Now that d you have to know, you have to figure out somehow, and so this is something you have to look up in a table or have some experimental data on what these collision cross sections are. Okay, so then what we want to know is how many collisions are happening in a given amount of time, and so that depends on how many particles are inside of that cylinder that's being traced out, and so we can write this out mathematically as the number of collisions is going to be equal to rho. This is the density, the number of particles per volume, times that volume. Okay, and so that's going to be rho times the collision cross section, right? So that's the area on the one side, and then we need to know, how as this particle moves, we'll take the average speed times the amount of time, and that'll tell us how far in distance it goes, right? So this is the area times the length. This is our volume. And we have a time component here because it's as the particle moves that gives us, the length of this cylinder. Now, we know the average speed. That's something that we have from the distribution that we were looking at earlier. And so we can go ahead and substitute that in and write this as number of collisions per time. So we can say dn collisions dt. So we just divide by dt over here. This is what we call ZA. This is collisions per second. And this is equal to rho sigma average speed, but we can substitute in the actual average speed that we know is 8RT over pi times the molecular weight to the 1/2. Okay, now this assumes that none of the other particles are moving. To add in that relative motion of the other particles, we can show, we're not going to prove it here, but that the average relative speed, because what we care about is how fast are the particles moving compared to each other, right? If we have two particles moving in the same direction, the relative speed will be equal to 0, whereas if they're moving directly towards each other, the relative speed would be twice the speed of each individual particle because they're moving fast towards each other. And we can also consider sort of the average case would be that maybe things are moving perpendicular. And this is not a proof by any means, but this kind of gives you an idea of where the mathematics is going here. This would give you the square root of 2 times u. And we can show that u relative, the average relative speed, is sort of that case, and where you end up with the square root of 2 times the average speed. And so that square root of 2 just gets factored in. And so our average collision frequency, ZA, is equal to rho times the collision cross-section, and then square root of 2 times the average speed. And again, we can use that average speed that we've calculated before.